So Barbara, if you could share the screen, that I think. How does this work now?
Does this work? You see it?
I can see it, yes, but the others can't yet see it. I still need to somehow move you to the other screen here. So now, can everybody see? Yeah. So, Barbara, we can now see your screen and you.
And this cursor also?
The cursor we can also see, yes.
Okay, perfect. Okay.
Here as well.
Sorry,
I make you as loud as I possibly can because we don't have a good loudspeaker here. All right. So.
Okay.
Yeah, please go ahead.
Okay. Thank you. Okay, so sorry for not coming there. Actually, it would have been much nicer to be there in presence, but okay, let's do it like that. So actually, we didn't start working on this project. So what I would like to do now is to tell you a little bit about our background, which is, I think, particularly relevant for this project would be entanglement theory and verification of quantum devices. So what I would like to explain now a little bit is how I see that we could possibly contribute to this project. And we is this group of people. We have been working a lot on entanglement theory, in particular Connie, Nikki, and David, and also on verification and benchmarking of quantum devices. We are currently also working on quantum algorithms and have been working on that. But I think that central for the discussion here is our expertise on entanglement theory and also on verifications. So verification, this has been together with Jose Carrasco, who now moved to Berlin, and Mark Langer, who is a PhD student. And Tristan and Matthias are also getting interested in this verification thing. So Mark and Matthias and Tristan are actually here in the audience. Okay, so what I would like to explain a little bit is somehow what we somehow know a little bit about entanglement theory and how we might be able to use these results also for the future. And to talk about the verification of quantum devices. And there you will see that we have somehow a completely different way of thinking about this verification. So entanglement, we have heard about it already today from Dieter's talk or Dieter's tutorial, where he was telling us a little bit about bipartite entanglement, even though he was using this idea of bipartite entanglement to construct multipartite entanglement, namely this MPS, but he was telling us about the Schmidt decomposition and so on. And the point is that in a bipartite system, so when we have only two quantum systems, then the Schmidt decomposition is actually everything that you need to know to characterize entanglement that is contained in that system. So in order to characterize these strong correlations that we have quantum mechanically, it is for pure state sufficient to look at this Schmidt decomposition. And bipartite entanglement is also because of that very well understood. So we understand also in the mixed state, understand pretty much what it means that systems are entangled. And we know what kind of applications we have. Okay, and there are very important applications that result from bipartite entanglement. Now, if we go to more systems, then of course everything becomes much more complicated because we have now a superposition of exponentially many terms. So if we have, for instance, n qubits, then we would have exponentially many possibilities here that we could all combine in one state. And when we talk now about correlations or entanglement in such a system, then we need to understand what each and every coefficient here means, and what it means that you change that, and what do you make the system better or less, more or less entangled, or can you use it for something else, or is it more difficult to simulate in such a or generate such a state and things like that. So this is actually the fact that we have exponentially many possibilities makes things very, very complicated. Also, when you talk about entanglement contained in such a state. But on the other hand, we all know that this is also where the power of our quantum computer or quantum device comes from. And so one big aim in quantum information theory, which is our background, is to understand what is multipartite entanglement and how can we actually use that, how can we understand it better to also kind of predict the behavior of, for instance, a quantum many-body system. And so when we talk here about the context that our project is about, and also, of course, for us, it will be relevant at some point to understand the entanglement that is contained in our system. What I mean by that is the one that we generate during a computation. And one of the obvious reasons why we need to understand that is because if we wouldn't have any entanglement, then we know that we can do the computation classically, efficiently. And so this now really separates whether we can do it efficiently or not. This does not prevent us from, or does not relate to what Dieter was saying before, when we want to compare the computational complexity, for instance, and we just want to see like a quadratic separation. Okay, but still, I mean, we know that, okay, if we wouldn't have any entanglement during our computation, then we could do everything on a classical computer. So we need to understand that, and what would be much better even is if we understand what kind of entanglement we generated, because this might then allow us also to even improve our methods. Okay, so by understanding the correlations that we have generated or the correlations that make the process somehow more efficient, we might be also able to improve them. What is also very important is that, again, I mean, despite the fact how Dieter put it and also wrote it very explicitly in the proposal, that our aim is not to realize quantum advantage, but just to show that we would have quantum advantage if there wouldn't be any error, which I think is very important that this is included like this in the proposal. But of course, we have to deal with realistic situations, which of course do have errors. And so what we want to do here also is to use maybe the insight that we have about entanglement to verify our device, so to check our device and to get some insight in how good our device actually works. And so this is why multi-body entanglement will be important in all these kind of quantum computations and quantum information theoretical tasks, and also beyond, well beyond that, thinking about all these quantum many-body systems and so on. So what we did, and I'm not going to bore you with this, but what we did in the abstract entanglement theory is really try to understand what multi-body entanglement is. And what we were able to show after many, many years of research is that if you really want to sort the entanglement that is contained in an arbitrary state in your Hilbert space, of many, many qubits, arbitrary size and so on, you want to do that if you want to be able to say that one state is more entangled than another state with respect to any entanglement measure, then you can actually prove that this is not possible. So I mean that for almost all states, this is impossible to do. And so this means that somehow to identify somehow the best resource, the optimal states, the things which you can do everything like we have in the bipartite case, is actually not possible in a multipartite setting. And so these very abstract and mathematical results clearly suggest that what we should do is to focus on physical relevant entanglement. And this is what we are currently working on. So we want to understand the entanglement that is contained in like subsets of states that play an important role in physics, or like, I mean, this could be matrix product states, stabilizer states, and so on. Or to understand like what drives, what happens in a phase transition, what kind of entanglement somehow sees that there is a phase transition going on, and things like that. And so with this, we want to get much more insight into multipartite entanglement, I mean, in the kind of entanglement that is really relevant, and also to understand new applications with that and so on. For the other thing that is related to that, which is to understand the physical relevant entanglement, is to see or to use entanglement as something that allows you to check how well your system works, how well your device is actually operating. And so I will come to that in a second, what I mean by that. So now I cannot change. Okay. So this is basically all that I wanted to say about pure somehow multipartite entanglement. But as I said, I will come back to that soon when I will use entanglement as a method to detect or to check and to verify a quantum device. So now I want to talk about this verification of quantum devices and of quantum computations. Okay, so the first one is somehow more general. And what we are dealing with are the main problems that we currently have in our NISQ devices. So first of all, our NISQ devices are small. There are a few hundred qubits, maybe maximum, and several hundred gates. And second of all, and this is very important, is that we, of course, do have errors. And when we consider errors in our system, then we lose kind of the advantage, because we will use entanglement, we will lose the possibility that we have superpositions and we are somehow going back to the classical world. And so what we have to somehow deal with is how are we able to characterize our small quantum devices, and how are we able to show that we can actually use them to do something useful. And so when we have now a quantum device at hand, and we go back a few years, then we had very small systems. And for these small systems, it was possible to do what is called state tomography, which is simply to measure the whole density matrix. So you measure the density matrix to show, for instance, that your device was able to create entanglement. And so this was a kind of a check whether you are able to control the system well enough to generate entanglement. So you really have quantumness. And this was feasible to check that by just making enough measurements. And at that time, it was possible to do that. Now, when we have like 50, 60, 100 qubits, this is no longer possible. So it's impossible to do state tomography and also gate tomography. So it's impossible to learn the whole density matrix, simply because we have exponentially many parameters. It's also very difficult to think about how can we detect an entanglement, because there are so many different ways of entanglement. So there are different kinds of entanglement, and one has to specify what kind of. We could focus on bipartite, but even there, it is difficult to see what do I have to measure to ensure that this system is really entangled, let's say, in some particular cut. And so the question that I would like to talk about now is, okay, so how can we actually do that? So how can we at least show that we have some kind of quantumness in the system? And then I want to go beyond that, and I want to say that, well, at the end, I mean, we are building these kind of devices because we want to use them. So we want to do some computing or some quantum simulation. And the question is, how can we then verify that? So how can we let our system now, for instance, run our algorithms and then get some measurement outcome and then be sure that this is really what we wanted to compute? Maybe this is something completely different due to the errors. And so to check how good the quantum device is, you could ask, okay, well, first of all, is it quantum? Can it generate some quantum resources such as coherence or entanglement? And again, when we talk about entanglement or how we can detect entanglement, then there are, from a theoretical point of view, many ways of doing that. There are several methods of how you can actually detect entanglement. But the problem is that we have to deal with, or we're dealing with NISQ devices where we cannot easily apply them because we cannot do tomography. Okay, so we have to find somehow more efficient ways to actually detect entanglement. And so this is what I would like to very, very briefly just mention. The two results, which I think that also in the tutorial of Dieter, it came up. This might be also useful here, because one is related to the detection of bipartite entanglement and the other one of entangled phase diagrams. And so when you have now a large system, and large, I mean something like 10, 15, 20, whatever qubits, and you want to somehow make sure that your system does something that is non-trivial. So there is some kind of quantumness, which is, for instance, bipartite entanglement. Then what we recently did, and these are some kind of papers that have shown this, is that you can make some measurements and you can use these classical shadow techniques, which is a way of, very roughly speaking, making measurements to get out of the classical information some kind of copy of the quantum information. So what you do is that you want to reconstruct the density matrix, but not with making exponentially many measurements, but actually much less. Okay, so you get an estimate of the density matrix. This is the idea here. And this has been introduced a few years ago. So either these classical shadow techniques or the randomized measurement by the group of John Preskill and Richard König and others, and also Peter Zoller and Andreas Elben and others, that have been working on that, ways of how you can actually reconstruct it. And so there are methods now that you use these kind of ideas and come up with some kind of inequalities that are easy to measure, because these are just involving some few moments of some of the partial transpose of the density matrix, not important the details, but this allows you to derive a method that you can actually really check even on the larger system. So you can make these measurements, it's sufficient to not do really that many measurements, but much less. And in this way, you could at least show that your quantum system or your quantum device is able to generate entanglement, which is a kind of a check of the power of this device. Another thing that I wanted to mention here briefly, and as I said before, this came up even today in the tutorial, is a recent result where we showed that with similar simple measurements, you can actually do also other checks, which are related to what is called entanglement phase diagrams. Now, without entering the details, you can show that this simple function here, which is just involving the second, the third, and the fourth moment of the partial transpose of the reduced density matrix. So it's a very, very simple function, and you can measure it. The behavior of this function as a function of your system size that you consider, and also the size of the bipartite splitting that you consider, shows a very, very different behavior depending on whether you have Haar random states or you have, for instance, matrix product states. So we talked about this already today in the morning. And so when we want to see, for instance, that, okay, so our algorithm generates this kind of states or does not, so goes really to Haar random states, does something random, or even does something that is actually classically efficiently simulatable, then you could use this measure to gain some insight into what is actually going on in the device. Okay, and this might be useful because you even see here some kind of phases that depends on the system size. So this is some kind of check in what might be able to use also in relation to what we heard today in the morning. Now, when we talk about verifying quantum computation, we really talk about I'm using the device, I'm getting an output of a computation, and I want to see whether this is correct or not. So the situation that we have in mind here is now really that you have Alice that wants to solve a certain problem. She sends the problem, like for instance, factorize a number to somebody who has a quantum device, Bob, and she gets some outcome. And the question now, very general question is, given that outcome, can I be certain that this is correct? And in our simple example, we can be certain because we would just take the outcome, 5 and 5, multiply it, which is something that is easy to do, and check that it's correct. And so the question that we have to ask is, what happens if you get 2 and 3 as an output? Well, in this case, it's not a problem because you can check that 2 times 3 is not 25. So you know that the output was wrong, and you would just rerun or redo the computation. But what if we use now our quantum device for like what you have in mind, that you apply some kind of circuit, and then at the end you make some measurement. Okay, now you get some output. Let's say that you get the output 0. And so the question now is, okay, so how can I actually check this? Now, from what we have heard so far, what you have in mind are mainly these variational algorithms, where this is actually not a big deal because you get some numbers or you get some parameters, and you can check whether with these parameters, with these answers, or with these states that you have obtained from your quantum computation, whether you reach a certain low energy or not. So this you can still verify by yourself. But imagine that you use now this quantum computer for a problem where you cannot verify it anymore. Okay, so this is really a problem that is efficiently solvable by the quantum device, but it's not possible to check the answer efficiently. Okay? And it's really that you want to have that answer. It's not that you want to be somehow close to some minimum or something, or have some low energy, but you really want to have that answer. And this is the question that people have been asking themselves many years ago. And one has to differentiate here between two scenarios. One, where we have access to our device. So we either really the people that are operating our quantum device, or we trust the people, like we trust IBM and we use their computer and we believe what they are saying. And the other case, which is also very relevant, is that when we don't trust them. Okay, so we use, for instance, a cloud computer, IBM, but we don't want to trust that the output that they give us is really the output that was obtained by the quantum computer. And so then the question is, in these two scenarios, what can you actually say about the correctness of this device? Is it even possible to use this device? Okay, or do you always have to rely on that the answer, okay, might be correct or not? So may I just ask, are there any questions? Because I don't see any of you, and so it's kind of hard.
At the moment, I can't see any questions, but I will shout.
Okay, very good. Thanks. Okay. Okay, so these are the kind of scenarios that people were considering, and now, because it's already late, I think that I might not go now into the details here, although I find it a super interesting problem, which has now recently found a solution, and it's not by us, it's by Umila Mahadev and Umesh Vasirani and Thomas Vidik and other people that have come up to us with a solution to this problem, which I think is really beautiful, which is that you're actually using a quantum device that you don't trust. Because you have some cloud computer and you run some kind of problem, like some most general problem that is efficiently solvable by a quantum computer. At the end, you make some measurement, you get an output, 0 or 1. And you can show that by purely classical means, so me and you can check whether this answer is really correct. And you can do that despite the fact that you can neither do this computation on a classical computer, nor is the problem a problem which allows you to check the answer efficiently on a classical computer. Okay, and this is really a beautiful result in my opinion. Just very briefly, the main idea is to use what is called interactive proofs. The main idea behind that is, okay, so you can imagine that if we as a classical user want to check the performance of a quantum device, it is much, much more powerful, and it does solve a certain problem that I have no chance to solve, and it does give me an answer that I have no chance to check whether this answer is correct. It's very challenging, right? And the trick is that you're using this quantum device and you're doing some interactive proof, which means that you are asking questions to this device. Okay, so during the computation, you are asking those questions, and in this way, you force the quantum device to make some commitment during the computation. Okay, and with this commitment, the point is that whatever the quantum device gives you as an output later on has to agree with this commitment. Okay, so and this prevents then the quantum computer from cheating. So this is a very nice idea that it was out already quite some time ago. The problem was that in former times one had methods of how to do that when Alice, the user, is using actually quantum devices, not classical devices. Okay, so if you can send like single photons and so on, then you could do this check. This is what is known, for instance, under blind quantum computation. And recently, as I said before, this has been shown that you can do that purely classically, and the idea here are the so-called post-quantum secure trapdoor functions. So these are functions that are hard to invert even for a quantum computer. And this, together with these interactive proofs, allows you to show that you can actually verify the output of a quantum computation purely classically, by purely classical means. And so this is something that we have been working on recently, also kind of implementing the first steps towards this on an ion trap quantum computer. And I'm saying that here because I think that, I mean, knowing this kind of ideas and also this quantum post-quantum secure trapdoor functions and these ideas, I think is very interesting because they have many nice applications that maybe it's good to have it in mind, that this is some interesting notion that can be used. Now, the last few minutes, let me briefly come back to the other scenario where we do have access to the quantum device. Then, of course, the situation changes completely. No? If we are the ones that are operating the device, or we can run tests, we can somehow estimate our error model, we can check that our error model is actually correct, we can estimate the errors, and then we can also work on this device to improve it. And so it's a completely different situation. It's not that I'm getting some output and this is the only thing that I get. No, I can really run tests and even verify my error model. And so there are many methods out there that allow you to check whether your quantum device is doing the right thing in case that you have actually access to the device. And so just from a very somehow general point of view, what can we actually do? So if we compare it to a classical computer, what can we do with a quantum computer? And what we can do, similar to a classical one, is of course to check the correctness of the output by running it, or by doing certain computations that we can easily do, and then we can also check classically, like multiplying numbers or adding numbers and things like that. So this is something that we can verify the output because we can do the computation classically. What we cannot do is to somehow trace. So we cannot open the device and look in the middle of the computation what's going on. Right? So this is not possible, which is a big contrast to the classical computation. But what we can do is to run our simulation, our computation on a small circuit, so with few qubits, because this is still something that we can test classically. And then we can check how good is the outcome. So important here, of course, is what I said before, that we are not working with a quantum device that doesn't have any errors. If this would be so, then we could simply run tests where we only test problems that are in MP, which means that the answer can be checked efficiently by a classical computer. As we do know that we do have errors, and this is unavoidable, then we have to deal with coming up with methods to estimate the error that happens and to show that the error is small enough so that we can really use this device. So this is the challenging thing here. So we know that our computer has errors, but nevertheless, we want to be able to use it. And so what has been done, for instance, also in the Google experiment, is to come up with an error model, use the quantum device for small system sizes, for simplified circuits, test it, verify that that your error model is correct, and then anticipate that the error model also works if you go to now a circuit that you can no longer run classically. Okay, so the supremacy circuit, so the one where you really outperform the classical device, you assume that the error model also holds there. So this is the idea. And what we follow here is something slightly different, because what we want to do is to use the fact that there are certain gate sets that have the property that if you would only use this kind of gates, so if you have circuits that are only composed out of these gates, then you can simulate them classically efficiently. But on the other hand, one can show that if you add some additional resources, so for instance, some other gate or some states that you could use, some entangled states actually, well, or even product states, depending on the scenario that you have in mind, then this whole computation becomes universal. And so what we do, and what we're currently working on, is to use that for verification. So what we want to do is to construct circuits that are, on the one hand, classically efficiently simulatable. This is what we need to have in order to estimate the error, right? We need to know what is the exact value to know what is the error. So they have this property, but on the other hand, they're very, very similar to the original circuit, so to the universal quantum circuit, so that you can expect that the errors of these two are very similar. Okay, and what we are using here are what is called as a strong and weak simulation of the quantum computation that we are doing. So you want to take an arbitrary, so for instance, you want to run some circuit like the ones that we saw today, and you want to see how well can your device actually realize such a circuit. Then you can use this circuit, you can rewrite it. So right out of the circuit, you construct another circuit that is very similar to the original one, but is classically efficiently simulatable. Now you run that circuit, you estimate the error, doing the measurement on the computer, you do the calculation on the classical computer, you compare, and you estimate the error. And in this way, you want to gain confidence that actually, if you run now the original circuit, that you would have a similar error. And so some nice circuits that have these properties are, for instance, what we called a few years ago, these validating circuits, that simply use the property that if you have now a universal circuit, then you just have to reorder the gates, okay, in a certain way. You just change the order of the gates, then you can make it classically efficiently simulatable. Okay, so I'm using exactly the same gates, but just in a different order. Then it would be classically efficiently simulatable, and so you can use that to estimate the error. Another approach is that you can show that if you can do an arbitrary computation on some kind of input states, and then with some restricted gate set, and if you change now the input state really very slightly, then you can simulate the computation classically efficiently. So you have actually exactly the same algorithm as you have on your quantum device, the supremacy circuit, or however you want to call it. You apply exactly the same algorithm, but to a slightly modified input state. And with that, you make this whole computation classically efficiently simulatable. So you can use that then to estimate the error of your quantum device. And so these are the kind of verification schemes that we have in mind and that we are working on. And okay, so one has to see how well this matches now with the whole project, but somehow the idea is to use these kind of schemes to see how well we can actually realize a circuit of interest on the quantum device and how well we can actually check that this is really doing what we want it to do. So to conclude, I was very briefly telling you a little bit about our background regarding multipartite entanglement, and that there might be some ways that we can use already some of the existing results or maybe extend it to see what kind of entanglement we generate in the process of our algorithms that we apply, and whether there's any kind of special kind of behavior, whether we see some kind of phase transitions and things like that. And on the other hand, I was talking about the verification of quantum devices and quantum computation, where for the verification of quantum devices, we could try to think of coming up with some methods of detecting some kind of special kind of entanglement, or also randomness, or kind of special kind of randomness, not necessarily high randomness. And then I was telling you a little bit about the verification of the output of a quantum device. Okay, thank you for your attention.
Thank you very much. The next what I do is I turn this camera around so you can see the audience. Is this working? Yes. So are there questions? If not, yes, we have.
On the checking of the quantum computer on the cloud.
Yes.
Where you said that you ask the quantum computer questions and they will answer. Can I see that like some incomplete measurements in between, or what kind of questions do I ask?
No. So so you can phrase every problem as a decision problem. So you want to know, is the answer yes or no? Okay. Whatever problem you have in mind, you can always formulate it like that. So like, for instance, you say that, because if I implement some simple example related to our topic, that if you implement this circuit and you measure now at the end, like one of the qubits, is it in the state 0 or 1? Or you measure at the end the energy, is it below a certain value or above?
Okay, so I would run some decision problems before I run my final goal simulation.
Before you run, sorry?
Like if I want to verify the computer before I want to put on the problem I really want to solve, or do I reformulate the problem I really want to solve in a decision problem?
Yes, you can formulate any problem in a decision problem. So this is why when you...
But I think, Barbara, the question was, when do you ask the decisive question, the one that you actually want to know about? So in other words, when do you just kind of listen the computer out to try to find out whether it's cheating or not? And when do you actually ask the question that you want to know about? Like in human interactions, you do exactly the same thing. You ask a few questions, check out the guy, and then you ask the question that you actually want to know about, and then you ask some other questions again.
No. It's really the output of the computation. So you can formulate everything as this decision problem. So this is
but it's not just one, you said. You have to ask a couple of questions.
No.
It's not just... Yeah.
You're interested in the output of one computation.
Right.
And now I can always formulate this as a decision problem.
Right.
So at the end I have a circuit and I want to know, if I measure now this qubit, is it in 0 or is it in 1?
Right.
Okay. And of course this comes with probabilities and so on. So this is clear because we're doing quantum computation. But
right.
at the end it's basically that. And so now I want to know this answer. The question is, suppose that I use now a very powerful quantum machine and it gives me the answer 0. Then what should I do with that answer? I cannot check that the answer is indeed 0, right?
Yes.
So what should I do? Should I trust it or should I not trust it? Or what do I do with that outcome? That's the outcome of any kind of problem that I want to solve, okay?
Yes.
It's really, you're using the quantum device and you get an output. This is the perfect thing that you want. But what do you do with that output if you cannot verify that it's really correct? So if this is, right? And so this is the problem. You want to check that this output is correct. Now, the way you do that, and this is why you say you're asking several questions, is that you have, this is complicated, right? Because you now, as a classical user, you're sending just questions to this, or you're asking this quantum computer for answers of other problems, of other questions, right? So a simple way that I like very much to explain is the following. If suppose that you tell me that you are very powerful and that you are able to count the number of leaves of a tree, okay? And suppose that I'm not at all powerful. I just have a piece of paper and a pencil, nothing else. Now I'm asking you how many leaves are there, and you give me now a huge number, okay? Then what can I do to make sure that you are able to count the number of leaves? What I could do, sorry?
You remove one and ask again.
Exactly. So I would blindfold you. I would remove a few of them and then ask you again. Because I can compute the difference of these two numbers. This is easy. This I can do with a pencil and a piece of paper, right? And if I do this sufficiently often, then I'm getting very convinced that you are able to count the number of leaves if you always give me the right answer, right? So also here, your answers have to be consistent, right? You're committing to the first answer that you say, And then it has to be consistent, because the rest I can check. And so this is, I mean, somehow the idea of these interactive proofs. Now, the fact that we test a quantum device, of course, makes it much, much more involved. And this is also why I think it's really very beautiful, this solution that they have found. Again, this is not us, this is other people. That it's really using the research of 10 or 15 years, where everything that has to do with this local Hamiltonian problem, all these things enters in that solution. Okay, so you reformulate your circuit into something into some Hamiltonian, then you have to show that you are able to generate a state that has an energy of this Hamiltonian below a certain value, and this is actually how you can, at the end, indeed verify that the output was correct. Okay, so this is not something that is. So I think that the main ideas can be explained, or at least I'm trying to, with these interactive proofs. But of course, the whole protocol is very involved, because you as a classical user, so as somebody who doesn't have a lot of power, checks the output of something that is very, very powerful. Okay, and it checks it really by just sending classical information. But it works, so this is what is nice. And this, yeah.
Yeah, maybe just a sort of follow-up question. So if I have one of these verifiers for using this interactive proof idea, can you use it on sort of an actual physical device, like say on the Google supremacy experiment, or is that just like a different class of a problem that cannot be verified in this way?
So, I mean, what you, in Google experiment, I mean, what you do there is really, you have these random circuits, right? And you sample. So what you want to do there is you sample from the output probability distribution. Okay, so this is not this is not a decision problem in this sense. You really want, in the Google experiment, you apply a random unitary and you measure all the qubits in the computational basis after applying this random unitary. And you want to know what is the output probability distribution of that. Okay, this is the thing that you cannot do classically efficiently. And so this is what you use your quantum computer for. Okay, so
it has to be a decision problem, but in principle you could, like it's still somehow more powerful than checking it. Like these other approaches you were talking about on a physical device, it would be sort of less powerful in this, because this can immediately tell you whether the decision problem is correct. Whereas these other ways are kind of interpolating and sort of trying to convince yourself that it's correct.
Yeah, so I'm sorry, but I mean, I hear you very, very badly. I didn't really get now the question.
Just that the interactive proof is more powerful than the second verification, at least for these very specific kinds of problems.
Yes, with interactive proof, you can use it for any kind of decision problem. You could now, I mean, like I said before, like when you say that we want to check whether the energy of your Hamiltonian would be below a certain value, you can always reformulate this thing as a decision problem. Okay, you do a binary search. So